Hello YouTube, PowerMax here. Today on Tutorial Tuesdays, we're going to be discussing capacitors. Now you'll see there's all different kinds of capacitors here, and they all have different applications. Alright, so here's the basic capacitor. Notice that there's only a few things needed to make one. A dielectric material, and two separated electrically conductive plates. Alright, so now you're probably wondering what do capacitors do? I mean, you probably have a vague idea if you've done anything in electronics hobby. You know that they kind of tend to smooth voltages out, and you generally use them to filter power supplies or make oscillators of some sort. But, how do they work? And why do they act like little baby batteries? Well, basically, capacitors resist change in voltage. In other words, if you were to put a voltage potential across here, the capacitor would charge up, but what happens if you try to change the voltage? Well, a current is going to be either entering or leaving the capacitor. So let's say that we charge this capacitor up. I'm going to put a whole bunch of red dots on one side to indicate a positive charge, and a bunch of blue dots to represent a negative charge. When there's a voltage potential across this capacitor, you create an electric field between the two plates. So in order to change the voltage on this capacitor, you have to either put more electrons into it, we have to cram more electrons onto one side and pull electrons out from this side, or we have to cram more positive charges on this side and take the electrons out on this side. So that brings us to one of the most important properties about capacitors, and that is capacitors resist changes in the voltage across them. You can see that the current that is either entering or leaving the capacitor is directly proportional to the change of voltage across it over time. dV dt is just a little calculus term which just means the slew rate, how fast the voltage changes with respect to time. So in other words, the change in voltage across it over time multiplied to the capacitance will tell you how much current is entering or leaving the capacitor. Likewise, if you measure the current leaving or entering the capacitor, you can figure out how fast the voltage is going to change over time. Well, nothing beats a good old-fashioned demonstration. So I built up this little circuit here, which is going to apply a forced variable voltage across this capacitor, and I've got two little LEDs here which are going to indicate the direction of current flow. And the brightness of the LED will be kind of proportional to the current going through them. Anyway, watch what happens as I change the voltage on the capacitor. You'll notice that as I increase the voltage, one of the LEDs lights up. And notice as I decrease the voltage across the capacitor, the other LED lights up. Now if I change this really fast, you can see how bright I can make these LEDs. Alright, now let's take a look at this voltage and current characteristic of a capacitor on an oscilloscope. I've got my Rigel DS1054 set up in roll mode, and I got my voltage graphed on the yellow trace, and my current graphed on the blue trace. Watch what happens though as I start changing the voltage. Notice if I change it slowly, the current doesn't really do a whole lot. But as I start to change the voltage really quickly, you'll notice that the current starts to get more and more aggressive. Alright, now let's take a look at capacitive reactance. The black curve represents our voltage over time. It's just a sinusoidal wave where the frequency increases as we go that way. And the red curve represents the current through the capacitor. And you can see as we increase our frequency, the current through the capacitor just gets insane. Now here's why that's happening. Notice that if you have a really low frequency wave, like say 1 Hertz, the voltage over time doesn't change very fast. At least compared to here where the curve is very, very steep. Anyway, and you can also see that at the peaks of the waveform, the slope is pretty much minimum. And that's the reason why the curve for the current looks the way it does. Notice right here at the beginning, our slope is basically 0, so the current through the capacitor is also going to be basically 0. And as we move along, and we start to cross over into the positive region, our slope becomes kind of steep positive. And our current is going to reflect that, it's going to actually peak right there. And as we reach the top and we flatten out right there, again our current is going to go right back down to 0. And you can see what the current does. I mean, as you go up in frequency, the current just gets ridiculous. Anyway, this curve right here represents the exact same thing, just graphed differently. It's graphed with frequency on the x-axis and impedance on the y-axis. Notice with this graph, if you were to look at just one frequency by itself, say 1000 Hertz, which might be right here. Look at the magnitude of the current over time, and look at the magnitude of the voltage over time. If you compare the two, you can kind of pretend like the capacitor is acting like a resistor if you ignore the phase shift also because, derivatives of sine waves and things like that, just kind of ignore that phase shift. You can see that the proportionality between the current and the voltage will change over frequency, and that's represented by this formula down here. Now our capacitive reactance, you can kind of think of this as resistance. And that's going to be proportional to basically the inverse of the frequency, how fast this goes up and down per second, times the capacitance. And so this graph right here is just kind of representing this curve kind of generically without real figured numbers here. You can see that as we increase in frequency, our impedance is going to drop. So what this ultimately means is that capacitors look like short circuits at really high frequencies, but they look like open circuits at really, really low frequencies. Alright, now let me actually demonstrate this. Like before, the yellow curve is going to be the voltage across the capacitor, while the blue curve is going to be the current through the capacitor. And down here in the very tiny fine print is the frequency reading of the yellow trace. So you'll see right now it's at 20 Hertz. And you can see our current is actually very small comparatively. But watch what happens as I start to increase the frequency. You'll see the current start to go higher and higher and higher until eventually we're exceeding the scales of the oscilloscope. So let's zoom in a little bit and let's zoom out of the current a little bit. So now it's 2 volts per division across a 100 ohm resistor. And let's continue to increase the frequency. And right around here you start to see some distortion. But that should give us a rough idea of what's happening. Alright, now let's look at some of the applications for capacitors. Now, foremost and most obvious is probably going to be energy storage. Capacitors tend to be okay at storing energy. They're nowhere near as good at storing energy as, say, a battery is. But one of the benefits of using capacitors is that they're able to deliver huge amounts of currents almost instantly because of their relatively low ESR, whereas batteries tend to have very high ESRs and can't deliver huge amounts of power instantaneously. So capacitors are much better for applications like pulse loads and stuff like that. They're also used for analog filtering, and because of the capacitive reactance, capacitors tend to be pretty good at not allowing DC current to pass through them, but allowing AC current to pass through them. And so you'll find their applications to remove DC biases on signals and AC couple things. They're also good at resisting voltage transients because, again, capacitors resist changes in voltage. So it makes sense that if you have a sudden amount of current that tries to go into the capacitor to raise the voltage, the capacitor is going to resist that change in the voltage and it's going to soak up all that energy. And because they're good at doing this, they're also used a lot in power supply design for filtering the voltage over time and giving a nice steady DC voltage. They also have a lot of applications for timing and counting. And if you were to, say, put a constant current through the capacitor, the voltage will go up linearly over time, or you can use the RC time constant, and you can make basic oscillators and things like that using capacitors, as well as data storage, because again, capacitors resist changes in voltage. And actually, this is how your computer memory works, like flash storage and stuff, is that you are actually storing charges on little field effect transistors, and their gates are more or less just little teeny tiny capacitors. They also have their use in phase shifting AC sinusoidal signals and motor starting applications. They tend to be used in AC induction motors to get them spinning and up to speed. These are actually motor starting capacitors, and that's exactly what their purpose used to be. Alright, so in conclusion, we covered what capacitors are and how they work by looking at their construction and understanding how charges can leave and enter a capacitor. We also covered the voltage and current characteristics of a capacitor and saw that how fast the voltage changes is going to be directly proportional to the current leaving or entering the capacitor. We also covered the basics of capacitive reactance and figured out that capacitors sort of act like frequency-controlled resistors. However, because there's a phase shift involved with it, and capacitors are essentially taking derivatives of voltage, there's actually a lot of exceptions to this when we start dealing with complex impedance. That is, anything beyond capacitor networks. So I'm going to talk more about capacitive reactance in the next video. We also got to see how many different possible ways capacitors can be used just because they resist changes in voltage. So next time on Tutorial Tuesdays, we're going to be covering RC networks, complex impedance, that kind of involves differential equations and imaginary numbers. Woohoo! We're going to be having some fun with examples, and we're going to learn about the limitations of real-world capacitors. See you in the next one! So if you like these types of videos, please like, comment, and subscribe.